All right, hello. Welcome to the first of hopefully many forays of mine into kind of low-level programming. So, a bit of background about myself. I work as a software engineer for currently a software startup, and it is a web-based product, so something that kind of runs in your web browser. I work largely with high-level and interpreted languages, primarily Python. I do jump into JavaScript where required. I mean, really, it's scripted languages in general, so I write a lot of shell scripts. I've also written various things in other forms of shell. Well, I mean, there's PowerShell. Done a bit of .NET, done a bit of Java, but I really am quite curious to start learning about really how computers work under the hood, really understanding them, and I would also like to increase my confidence with a low-level language in the meantime, and I feel like C is a good answer to that. So sound is a bit bombastic for my taste. I also feel like I'm competing with it, so I'm going to turn the sound down. I also have pretty severe hay fever allergies right now, so I probably sound extremely nasal, and if I do, I really am very sorry. But there's really not much I can do. I may even end up just completely giving up on this recording because I feel gross. I'm going to have to be blowing my nose a lot, but I will try and mute whenever that happens. I need to blow my nose now. But yeah, I feel like a very good exercise is I found this article quite a while ago. It was really all about how save data is structured in Pokemon games. So, just a brief kind of rundown. A Pokemon game, especially in Generation 3, is literally a ROM, or it's just like a random assortment of bytes that kind of happen to be a game that you can play when they're executed through the Game Boy's system, essentially. And a save file in Generation 3 is like a collection of bytes that, when put together, represent your save data. So where your character is, how many Pokemon they have, how many items you have, what does your PC box look like, what does your progress look like, and so on. So there's kind of structure to these bytes or these save files. And there's a very high quality write-up here on Bulbapedia, which is all about what save data looks like in the Generation 3 games, or the Game Boy Advance games. So you can see here that we have two game save blocks. So one of them is your primary and the other one is your backup. So if something goes wrong with one of the saves, then you kind of have a backup. As we can see, so if we have some kind of invalid data here, then the game will use the previous save. And if both of your saves, game save A, game save B, are messed up, then you are kind of forced to start a new game. And then we can see that every block of saves consists of what we call sections. So these sections have 3,968 bytes of actual data, and then some kind of metadata about that section. And then of those sections, the first one is your trainer info, then you have your team and your items, then you have game state, miscellaneous data, rival info, and then all of your PC boxes. So this is pretty cool, right? It kind of dives into what the checksum looks like, what the signature looks like, how you can calculate the checksum, and how we can detect basically which save is the most recent. That's your save index, and then this is what the Pokédex data looks like. So it's a very thorough write-up, and I need to blow my nose again. I'm actually just going to test something real quick. Okay, neither of these work. No, I don't think my OBS hotkeys work, so... Doesn't actually say if there's a pause button I can enable, which is really annoying because I was really like to pause when I have to blow my nose, but I'm just going to persist. I'm going to persist for like at least 15 minutes to take me into 9 o'clock. But yeah, here we go. So I basically want to do an exercise here, which is to see if we can do, you know, satisfy my inner child and see if we can generate a level 100 Mewtwo. So can we hack ourselves a level 100 Mewtwo? So how would we go about doing that? Well, we can actually kind of look at the sections that we need and, you know, eliminate ones that we know aren't going to be relevant, and then dive into the ones that we definitely are going to need, and also the functions and things that we're going to need to do as well, because save data is obviously checked for integrity. We have a whole kind of checksum that we need to deal with here. So obviously our team comes from this first section. So if we click on this link, I don't know why it's not taking me there. Is the link broken? Or it just links back to the page? No? Does it? Okay, alright, fine. Well, it is here. So if we go to section 1, we can see kind of a table of contents here as well, and we can see that it's slightly different for every game. For reference, the game that I'm actually going to be using is Pokemon Fire Red. So everything that we're looking at here, we're going to use the Fire Red and Leaf Green reference for. And I can't remember what's going on there, but I need to have an air purifier. I'm not actually sure if it works in removing allergies, but we'll turn it up. So there may be some background noise now because I'm suffering pretty bad. But yeah, this is the general idea. So we have a table of contents here, and so we clearly have, you know, 4 bytes of data which shows us the size of our team. And this is quite literally the number of Pokemon that are currently on the team. And then at offset 38, in this section, we have a 600 byte list of Pokemon. So probably a Pokemon itself has an actual... yeah, exactly. So data representing information for up to 6 Pokemon. So I'm assuming one Pokemon is 100 bytes as an array. For the format, we have another article which talks about the actual specific settings that we can set on that Pokemon. So these are things like its name, probably what the Pokemon actually is, yeah, who the original trainer is, and the attack, defense, speed, special attack, special defense, and so on. So this is our ultimate goal. Can we hack ourselves a level 100 Mewtwo? Now, I don't know the answer to that question, but I think we probably want to start by actually reading in the data here. So if we look, there's a section at the very top of this first article that says, unless otherwise noted, integer values occupy the specified number of bytes and are little endian and either unsigned or their two's complement. Text has a proprietary encoding. We're not massively concerned with text, although that may come back to bite us later. And somewhere it does say that everything is... Okay, it doesn't actually say about unsigned characters, but because these are bytes, these are quite literally just unsigned characters. And they are specific bytes of a specific size. So I'm going very much back to basics here. So let's see, although I probably could just use the man pages. So let me do that instead of doing web requests. So we want to fopen, we want the library. So we are in stdio.h, and we can see that we need a path and then a mode to our file. So first of all, what I'm going to do is actually just take a backup of this. I'll just call this .bak. So we always have something that we can go back to, and I'm actually going to make another hidden one here just in case, because I don't trust myself. Oh, we can't do it that in Finder. Wonderful. So, where even am I? And I can't get used to this keyboard. There we go. So, we want to CP Pokemon FAR, or Pokemon FR, back, PKMN, FR, .sav. Okay. So now if we go back to our fopen, we can see that we do need to give it a specific path. So let's go ahead and do that. And I'm actually just going to get rid of that first line. And what does it give us back? It gives us a... I think it gives us like the actual stream or null. Because, yeah, file is some kind of like built-in type here. So what we want to say, or rather it gives us a file pointer, I assume. So let's call this save data. And this is going to be fopen, and this first argument is going to be a path actually to our save file. So let's plug that in, and that didn't really work, did it? So let me just get rid of that. And then we need to also give it a mode, and this mode is going to be R for read. I'm not actually sure if the mode needs to... No. Okay, so we can just be R. And it probably would help if we maybe declared some of these types. So... oh, sorry, not types, but rather the sizes that we have here. So, I mean, I don't know actually if we can just use a size T. Yeah, let's do that then. So that is 57344. And actually, it's the same for B as well. Does it like that? Yes, it does. So let's start out small. And we have AI. Do we have AI? We don't have AI, but it has some full line code completion. What? Okay, this is a little bit annoying because I kind of wanted to do this myself, but yeah, sure. We'll take that handhold for now. Otherwise, we're gonna print F and we're gonna say no, we're actually gonna say save data loaded correctly. So let's actually give this a try and just see if we can at least like access the file, which we can. Save data loaded correctly. Perfect. Happy days. So I wonder if it's worth kind of maybe putting these into some kind of structure. The issue is I'm not really sure how we can do fixed size structures in C. I mean, I do wonder if maybe we need to declare these types outside, because I mean it doesn't necessarily need to be a struct, but we could say something like data. How on earth do we do type def? Type specifier missing. Let's actually see how we do. Okay, this is literally just an alias to something else. And then we just do the... Okay, so maybe actually an int, or not an int even, an unsigned car. Let's call this data, and it is data with a capital D, and it is 3968 bytes. Cool. And maybe we can do the same for section ID, which is 2. Then we have checksum. Signature, and then save index. And these last ones are actually 4. So now that we have those sculpted out, I wonder if we can actually create a struct based on this. Whoops. Which we can call save block. And this is going to consist quite literally of what we declared above. So we have a data, we have a section ID, section ID. Then we have a checksum, then we have a signature, then we have a save index. And it doesn't seem to be complaining about anything so far, so that's pretty good. Now, how do we initialize this structure? Well, the issue is a block like this doesn't necessarily represent the first bytes that we actually observe in a save file, although saying that, actually, I think in this case it does. And also something we need to be aware of, actually, is that some of these block sections are actually slightly different, or rather this is how many bytes should be validated for the checksum. So this is a 16-bit unsigned field and must have one of the following values. So I guess, oh okay, actually sorry, these are the numbers for the section ID. Or maybe what would be useful is if I actually demoed where I'm at in the game. So I've saved twice, which means that I have 2 save blocks. But I'm literally at the very beginning of the game. So if I load in here, it replays my steps. But we can actually see that I have a level 6 Squirtle. So happy days, we are in the game and we have some save data. So what might be worth actually trying to read here is maybe getting the save index maybe of the first save data that we actually have, and then we can get that from the second set of save data as well. So I'm actually going to prefix these with size gamesave A and size gamesave B. Or actually, I mean, we don't even need to have A and B. We can just say size gamesave. And then we can do stuff as well. I mean, I don't know if we're going to use this code necessarily, but this is kind of representing stuff here. So size Hall of Fame would actually be 8192, for example, but I don't really need to do that at the moment. Okay, so what's interesting here is that it looks like every piece of data that we have is actually 3,968 bytes big. But what I would need to represent when we come to the checksum is actually how many bytes of data we need to validate. But let's not worry about that yet. I actually want to just read the very first save index. So if we kind of like use the maths here, we know that at the very beginning of this file, we are instantly starting at game save A. And inside game save A, the first 3,968 bytes are data. The next set is the section ID, then the checksum, then the signature, then the save index. So we need to take that kind of sum total of bytes, or at least for the first section, i.e. our data of trainer info. So we can actually just jump to basically the latest bytes in those files, which should be at 0xffc. So we could jump to that in the file. So actually, literally at 0xffc is a size 4 set of bytes which we can read, and that would be our first save index. And then we have like a fixed point where we can jump to get the second save index. So that I imagine would probably work. What may really help here actually is to look at this in a hex editor to kind of validate what we're seeing. And I'm massively unprepared because I don't have one installed, but what I can do is open our save file, which pretty much doesn't have much data in it until you start really getting through the file. But what I am hoping is that actually at FFC, so much further down, we actually do have some readable data. So there's probably a go to, yes, a 0. Oh, can we type something in there? Does that let us? Oh, okay, go to 0xffc. And we can see that the first one is 02. So this is telling us that this is save number 2. And because we have 4 bytes, all of this data here is used for our save section. Now, this is little endian, which actually means that the smallest value is the first byte. So we're effectively reading, not backwards, because if this was kind of our number from left to right, it would actually, the 02 would be here. Because we're little endian, it's here first. So that's something to be aware of. Now, if we did the maths to figure out where in where we can get the game save B save data, we can also do that as well. So we know that this starts at E000, but if we wanted to go to EFFC, this should take us to our first this should take us to our save index, which says 01, which it does. Okay, so we can see that tiny blue square there says 01. So that is save index number 1. So it actually wrote to game save B first. Now, when I was trying this exercise a few years ago, and I knew just so little about C, I did actually get this far. So I did kind of know this quirk that when I save for the very first time, it saves to block B, but then for the second time, it actually saves to game A. And then when I save again, it will actually save to B, and this number will change to 3. And I feel like we can maybe prove that. So let me actually go back to my folder here. And I'm going to save this one to a copy. And what I'm going to do is open the game once again. And let's load in. And skip that. And then let's move down. And let's save again. Which I would. So there's already a save file. So we now have saved that data once more. So if we were to unload this file or just refresh it, you shouldn't have anything in here. Yep. So let's open this file and let's go to Pokemon FR. Then let's go to FFC, or rather 0xFFC. And we can see that save data 2 is still where it is. But if we go to EFFC, it now says number 3. It's incremented that save index counter. So we kind of know where in the file to read this data, which is pretty good. But if we need to start doing like arithmetic and things like that, it's going to be trickier because we need to load the data in effectively backwards. We kind of need to go to the end and then build up our characters and stuff. Or whatever, like, words we're loading into almost backwards, because this is our most significant byte, and we need to load this back, but whatever. It's fine for the moment. So we kind of know how to read the save index in a hex editor, but let's translate this to C, which should be, like, substantially easier. What we can do is say, so let's say, let's call this save index 1 and save index 2. And SI1 is going to be, not F, well, it could be fgetC actually. Although, how do we use fgetC? Oh, I mean, that is literally just loading the very first byte of the file. So that's probably not what we want, or rather, that's where we kind of are. So let's do fseek sav data, and we want to. How does fseek work again? So what is that last argument? Whence. And what is whence? Whence. The west doesn't actually say whence. Whence. Oh, sorry. The new position measured in bytes is obtained by adding offset bytes to the position specified by whence. Then the offset is relative to the start of the file, the current position indicator, or the end of file. So I don't really know why it was recommending me seek end. We would actually want that to be seek set. Yeah. So argument number 1 is our stream of data. The offset is where we want to go to, so that's going to be FFC. And from where is going to be seek set. So that's all good. And so this is moved kind of where we're reading. This has done this operation like the very first thing we did in the hex editor, which is the goto. So actually jumping to the specific offset that we want to read from. So if we load this file again, if we were to load this program, it's now going to basically perform that jump to here. And then fgetC is going to read that character and actually save that into this variable here. And then we want to do another fseek, and let's call this sav data. And we now want to go to EFFC from seek set as well. So from the start of the file, we want to jump to EFFC. So I could have done seek current, but that would have taken my current position at FFC and added and gone or I assume it would have moved EFFC number of bytes on from there, which is not what I want. I want to go from the start of the file, so seek set, immediately to this offset, so that I can actually grab this data here, and I can say SI2. So we know that SI1 comes from block A, so maybe I should have said actually A. So I'm going to call this SI. SI. Will it let me edit? No. SIA. And this one I want to be SIB. And now it's complaining at me, assuming I'm not using these variables. Yeah. So, I mean, does it have an autofix for that? Sure. Okay. So at this point in the program, we know that the save data is loaded correctly. And what I'm going to do is just print a new line there. And then let's do 2 new print statements, which say that the save index in block A, or rather block A, I guess section A? Yeah. Block A, section A is, let's get that value in hex, because that's how we were seeing it there. And make it print percent instead of printing an argument. Okay, it's just getting ahead of itself. And that's going to be SIA. Then over here, we want to say that the save index in block B, section A, or rather, let's call this section 1. Or let's call this section ID and 0, is the value of SIB. And then we want to compare which one is larger, so we know which game save is the actual largest one. So let's say if SIA is greater than SIB, then we want to say, let me just take another printf and steal that. We want to instead say something like save index in block A is larger. So block A is current save. And for good measure, we'll do a new line. And I pressed the wrong key. So then we can say else that the save index in block B is larger and block B is the current save. Now we could be a lot more clever about that, but I'm really just trying to do basic stuff here at the moment. So I feel like this should work. It's saying that this is const because we haven't changed it. So I guess it's const because we're never going to change it. So that's just the idea trying to be helpful, I guess. And let's actually see what this program does now. And I haven't done new lines here, which would probably help us. Would at least help us read a lot easier. So let's run this again. And we can see that the save index in block A, section ID 0, is 2. And we knew that that was at FFC. So if we go to FFC, in our save data, we know that that's 2, and then at EFFC, that is 3. So we have printed that out correctly as well. And we know that it's picking it up from the file, so that's absolutely perfect. That is 100% what we want. Okay, so we know that we can kind of skip somewhere in a file and actually grab some data out, and we can kind of do an if condition to see which is the most recent game. So I guess we could do something like initialize like pointer, which says which is our current block of data. But what I would be interested now is actually trying to load the sections into our into our actual save block. So I actually got this wrong. This struct is incorrect. This is actually save data. Oh, sorry, no, this is actually a section. And a save block is made up of specifically sized sections. So, or rather, it's a collection of how many? 14 sections. So, let's say section 14. So a type def of section of size 14. I'm not sure if it's going to allow us to do that. Is data. Okay, so it has an issue. I guess this is invalid syntax. So how do we get an array of structs? Because this is essentially what I'm doing. Let's see. Array of structs in C. Struct A. Oh, okay. So it may not actually be a... Unless it actually does need to be... No, surely not. Wrapped in a struct. No. That was worth a try. Okay. So that's that example there. So this is a struct, but I want to kind of say that we have something which is a fixed size. Maybe we just can't do that actually as a type alias, because... I don't know why. But I guess it needs to be actually in our code. It can't just be sort of like a global declaration, which I suppose is fine. So in that case, we want to initialize a game save block when we have successfully loaded our file. So let's do... I guess it would be a section block A. Or let's call this game save A. Is basically 14 sections. And then game save B is also 14 sections. Okay, so it's okay with that. Nice. So there's probably some maths, well, there would have been some maths that we need to do to actually load this data into the specific sections. But I guess we don't need to do that anymore. Now, for initializing this struct, or actually kind of like getting the memory for this, we probably want to do a call to malloc. Question mark. And it's auto added our stdlib for us. And I guess this is a pointer now. And we need to allocate... Or it doesn't recognize malloc. Alright, so what's the issue here? Change the type... Huh, okay. Maybe it's not a malloc. Because actually, I guess if our... Or we could just initialize like each thing each time and push that into the struct, but I don't really want to do that. I'd rather just kind of like read the bytes and be like, look, here's your template. Okay, let's see. Initialize struct with malloc C. Okay, it's actually the size of our... So they've got a struct game. With the function... Don't be misled by the return value of malloc. It returns a pointer to the allocated space. That's why it should be struct game new as it is. Okay. Oh my god, my allergies are just completely messing with me. Okay. Well, maybe if we actually filled out the malloc. So size of a section multiplied by 14. So it doesn't like that. Substitute type def. Is it because of that? It's the fact it needs to be a pointer. If I did substitute type def, what does that actually do? Nothing. Okay. Let's see. So, I mean, this Stack Overflow thread is just kind of saying, like, you can plug the values straight in, which could work. Maybe that's a cleaner way, actually, if malloc isn't the kind of go-to type. I mean, to be fair, maybe we could just do, like, function calls, right? Maybe it doesn't need to be malloc. Maybe I'm completely just... Maybe I don't know what I'm doing here. Maybe let's think before we do that. Let's actually try and just load specifically section A or section 0. So let's call this section 0 save A. Which is a... I guess it's a section, right? And then we can do... So our data is... let's get a string of characters. And actually, maybe fgets is a... Is fgets even, like, recommended anymore? Because I know there's always things about, like, you shouldn't use this, you shouldn't use that. I guess fgetC is okay. Or is it fgetS that it doesn't like? Okay, the getS is that... Okay, is it actually getS that it doesn't like? Yeah, the getS cannot be used securely because of its lack of bounds checking. Okay, alright, sure. Strongly recommended. Fgets is used in all places. So, this is saying, I guess, the actual place... Oh, okay, so fgets is where we want to read into. Reads at most the number of characters specified by size from the given stream and stores them in the string str. Reading stops when a new line character is found. So what was actually the difference between that? There isn't one. Okay. Well, actually, getS just had a character. Let me actually look at the manual for malloc. So allocates memory. Returns a pointer to the allocated memory. Okay. Yeah, maybe malloc is not the way. Let's do... Maybe let's try and do fgetS, actually. So, we know that we have... So we know that data is literally just a unsigned character of a certain size. So let's just call this sec0 data, and this is sec0 data is literally just an initialization of data. So I think we can just do that. So our fgetS so let's do fgetS. We have the string we want to read into, which is sec0 data. Then the size, which is actually the size of data. So that's going to be 3968. And we want to read that from savdata, which is our file, which is our stream. And I assume that will be okay. So then actually our .data is sec0 data. And then likewise, we can actually do the same for the section ID, checksum, signature, and save index. So let's see, section ID, sec0 ID. We'll initialize to something empty, and let's read into sec0 ID. And that is going to be 2 bytes. Likewise for checksum. And then the signature, and then the save index. And these are 4 bytes. So let's change those. That is my check0 signature, or my sec0 signature, and this is my sec0 save index, and this is my sec0 save index. So now that we've loaded all of that data, let me actually comment all of that out for the time being. We've kind of loaded things into individual structures, and what we should what we should be able to do now is read that first byte of the data. So we know that it's little endian, so the least significant bit is first, which contains the data that we want. So I guess we can actually do a printf and actually access data and see what's inside it. So let's say game save a section 0 let's call this GSA sec0 save index equals %x. And this is going to be our sec0 save index at byte 0. Cool. And this should give us the same number that we actually had before. So this is whatever is at FFC, which is 2. So hopefully this will work. And it says 0, so this is actually not correct. Okay, interesting. Did we do everything right there? So it read 3968 into data. It read 2 into section ID, into checksum signature, and save index. So Let's change that to whatever HHU is. Pointed to object. Oh, is that actually valid syntax? No, it's not. Okay. So, I mean, this is actually fine, but... Unless it's the last one in there? No, it's not. And then that's too big. So save index is 4. Index may have a value of 2, which is out of bounds. Okay. And our section ID is an unsigned character. Oh, hang on, not... I'm so dumb. Can you tell that, like, I come from an implicitly typed background? Alright, maybe that will work. I don't know why I just accepted that it was made up of two bytes. That's crazy. But this still didn't work, so that's fine. Well, it's not fine, but do want to see what's going on here. We also probably want to close that file before we finish. Game save A section 0. The data is 0. I hope that we haven't like damaged this file in any way. So if we actually go to FFC now, yeah, okay, it's still there. Right. So that is strange. I mean, surely there is kind of like a head in the stream that we're reading from. So the reading stops when a new line character is found or an end of file error. The new line, if any, is retained. Oh, actually, fgetS is get a line from a stream, which isn't necessarily what we want. So okay, so you can do get car, but I would rather do something that I can just enter a fixed size in and have it just completely ignore. Returns null on error or EOF, so can handle read or failure effectively. Oh, so actually it may be that these are actually failing, and because we're not handling them, we actually have no idea. So let's say... well, what does fgetS actually return if it succeeds? Return values, they will return a pointer to the string. If end of file occurs, Before any character is read, they return null. Okay, alright, sure. So, let's say... save index r. Let's just do that. If r is null, cool. Now it doesn't actually like this because it's not telling me why. So maybe when we try and compile, it will tell me. Oh, okay. We actually have warnings. We actually have many warnings. Passing data to parameter of type character pointer converts between pointers to integer types. Okay. Oh, this actually is asking for a pointer. So maybe we can just give it its... No. No. Okay, what is it saying here? Passing section ID, aka unsigned character 2, to parameter of type car star. One is of the unique plain character type and the other is not. I mean, these could just be actual characters, they're not necessarily unsigned, right? Oh, integer values occupy the specified number of bytes and are little endian and either unsigned or 2's complement. And then your section ID, 16-bit unsigned field. What does it say about save index again? It's just a number. It's just a number, but it is unsigned. So... how can we actually... Okay, I mean, these people are using malloc. I see, which is the usual. Oh, maybe I need fread. Do I need fread? Yes, it does. So we give it a pointer to from the stream pointed to by stream, storing them at the location given by pointer, and it reads n items. Objects, each size bytes long. Okay. Let's just try reading just the save index to kind of make things a little bit less complicated. So we know that we can do actually this fseek to grab the save index at A. So I'm gonna yank this line and actually just move it up here. So we know immediately where we want to start reading bytes. Whoops, I didn't mean to do that. And then, yeah. Now I think we can do our fread. So we also want to make sure that we can return it. Is a short object count or 0? So what does this usually give us back? Short object count. So is this an int? Oh, it gives us a size t. Okay, so size t red is fread that. Size of save index. Number of items 1. Save data. Yes. Okay. This sounds better for what we want. So then if read is not 1, then we want to say error reading save index as we did before. That actually needs to be a printf. and we'll just return 1. Okay, so this should work. It is complaining that this isn't const, which it is, I guess. So let's see. We still have 0. Okay. Okay. Let's see. It stores them at the location given by pointer. I wonder if it's because we're initializing this and we can't write it again once it's been set. I don't know. Or it might help actually if we read the first byte. I mean, that would be probably the most useful. Okay. Oh my gosh. All right. Yeah. I'm very new to this. Cool. There's no reason why we can't do the same for block B. But let's actually round off by trying to read the checksum. I think this would actually be a very useful thing to read. So let's just literally copy this code that we had here. And this instead is going to become a checksum, and this will be our sec0 checksum. I don't know if camel case is really like the convention that we want to use here, but let's go with it. So this is our sec0 checksum, and it's a size of checksum, and we want to read it from this thing here. And we cannot redeclare this, so I'm just going to use the same variable as before, and we'll just overwrite it. And then this one is actually going to need to be seek start. Was it seek start? Seek current or seek end. Oh wait, no, seek set. Sorry, seek set is the start. So we do actually. Sorry, no, we do actually want to keep them as seek set for both. But instead of FFC, we want to read into FF4. And then when we do the actual printf here, we can say the checksum value is this. But because this is 2 bytes, it may get more difficult to read if that checksum has evaluated to a number that's too big. So let's actually do something like this. And we'll do, say, it's not save index, but it's sec0 checksum 1, and then sec0 checksum 0. And then we do the same thing again, and this should show us our checksum value, which is 0C. So if we go in our hex editor to FF4, we can see that we have 0C, and then if that's our least significant, this would be our most significant, but it hasn't evaluated that. So we do need to be careful there. The checksum is 2 bytes, so it's these 2 bytes here, and this is our least significant value. So I do wonder what the section at FF8 is, if anything significant. It is our signature. And this contains 4 bytes in between the checksum and safe index. Holds the magic number 08012025 in little endian format, so it's reversed, as we can see. And if the signature is different, then the section and extension well, the section and by extension the save block is treated as invalid. So we could actually edit this and corrupt our save, but we don't really want to do that. Yeah, literally just magic number, another means of checking for integrity, I guess. So this is all fine. We can try and do some more complicated stuff later, but for the moment, I think I'm going to leave it there because time's getting on. So thanks for your patience. I'm very, very new to this. Started out very small, but it was fun, and hopefully I can do it again soon. Bye-bye.